This podcast is presented by HANNOVER MESSE, your leading event for industrial AI.
Hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and we have a very weird situation because normally Peter and myself record this episode, but Peter is traveling with an unreliable internet connection in Asia. So now we could have gone and clone his voice. Instead, Peter asked me to share some topics with you. First, a reminder from last week's podcast from Xiaopeng Li. He suggested that while the US and China have been leading in Gen AI development by building foundation models, the opportunity for European companies may be in creating value by applying foundation models. And we know since the weekend, we have a new foundation model. It's called Sora. And Sora and industrial use cases, how do they go together? Very, very fine. And Stefan Sufelak has explained it wonderfully. And I have a quote for you. So Stefan wrote, Sora is a glimpse into the future of engineering. Okay. The result of the text-to-video tool from OpenAI are not only amazing to look at, but they reveal an incredible understanding of physics, and that is important. I don't know if you know the video by Sora with these ships in the coffee cup. And what is fascinating for me and for Peter and for Stefan maybe also, the flags are waving in the wind, the ships moving along with the waves, light bouncing off the water surface. Very, very realistic. In order to render the scene, the model has to first implicitly construct 3D models from the text input. Compute the physics of the scene, render the scene. And now what comes together, these are 3 core tasks in most engineering workflows. 3 core tasks. And Stefan is absolutely right. Gen AI is not only for marketing, it's also for industrial engineering workflows. Wow. And one comment by myself, if you want to know more about the technology of Sora, I link to a YouTube video in the show notes. So, Peter is in Asia. I was in Austria to plan our event AI in the Alps. Thanks to HANNOVER MESSE for being our event partner. And our guests this year are Professor Dr. Johannes Brandstetter together with Dr. Sebastian Lehner. They will hold a workshop on simulation and AI. Our guests are Trustify. They will talk about certification. And our guest is Professor Dr. Marco Huber from Fraunhofer, who will discuss AI use cases. And one spoiler, we will have an episode on simulation and AI with Johannes in the next weeks. My news for today, I have a reading suggestion. A very interesting article for all decision makers in the industrial sector by Benedict Evans. It's called AI and Everything Else. More in the show notes. So that was it. I hope I got all of Peter's topics correctly. We will now move on the main part and hopefully Peter will have an internet connection by the next time. So Peter, all the best to Asia. Enjoy your holidays and see you, hear you soon. Bye-bye.
Hi there. Welcome to a new episode of the Industrial AI podcast. My name is Peter Seeberg and I'm your host. And my guest today is Behnam Nouri. He's the AI ML tools expert for knowledge-based engineering and platform design with Siemens Energy. Behnam and I are going to talk about design process acceleration by means of integrating machine learning. Hello, Behnam.
Hello, Peter. Thank you for inviting me.
You're welcome. Looking forward to what it is you have to share with us. Let's start with you introducing yourself to our Industrial AI podcast listeners, please.
Hello, my name is Behnam Nouri. I'm working now since 15 years on turbine optimization. I started to work with Rolls-Royce on a project called Virtual Turbine, where we virtualized the full turbine the first time. And then I switched 10 years ago to Siemens Energy, where I was responsible to building up big process chains, big multidisciplinary optimization process chains of high-efficient gas turbine blades and vanes. Yeah, and since 5 years, I'm more and more interested in integrating machine learning into our process chain because we saw there's a limit of computational time and what we really require to get a robust design. So we integrated piece by piece machine learning tools into our process chain to get the designs faster and more robust. And here we collaborated to Siemens Energy with Siemens Digital Industry together to create some products, which I will talk to.
Okay, good. Yeah, you and I, we met already at the first AI in X conference that Robert and I have started. It was actually the AI in what we call the monastery.
Yeah.
That was in Würzburg, right? And I do recall also, I kind of, from the very beginning that we met, kind of linked you always with turbines. And that's what I'm going to ask you. Maybe to give our listeners a small introduction into turbines. You just mentioned Rolls-Royce. The first thing I think, turbine, probably has something to do with these, can I call them engines? I don't know, but you will tell us that, make sure that the plane will fly. I think later on we're going to talk about gas turbines. So I think there's different types of turbines. What is a turbine and why will we later on be talking about them?
Yeah, a turbine is, in short, like a machine which converts mechanical energy into some sort of rotating energy, and then you can generate electricity, which we do at Siemens Energy, or at Rolls-Royce, we just generate thrust and push the airplane forward. And in wind turbine, it's working the same. So we use the nature, the wind, to rotate a big shaft and a generator and generate electricity. And the same applies for coal power plants. So there we have steam turbines.
Right. We're not going to go into the details of the politics behind it, but you already mentioned. So I think we concentrate maybe later on gas, but the same could be done, you say. And maybe you're going to tell us a little bit more about your company as well, and then we'll hear that. Wind or coal. And there was one that I heard about, and I just want to share it because I think it's rather interesting. You should confirm if that is actually correct understanding of me. But there is what I would have called 100-year-old project. I would have called it a water turbine, but I think the official English name would be more like hydroelectric power station called Walchensee, that's south of Munich, and that started exactly January 26, 1924. So what you then call that, and I do recall that I visited there maybe 10 years ago, and what I was seeing there, so where the water falls down, that would be a turbine as well, right?
Yeah, in the end, that's a water turbine. So you use the force of water and height difference to rotate the shaft and power a generator. In the end, the first power generation in the US and Germany were all driven by water turbines in the beginning. And then they started to use coal.
Okay, yeah. And now we want to try to move away from coal, I guess, towards wind and probably also still gas is what we're talking about. Okay, very good. Yeah, I recall that 100 years ago, and the guy who proposed it, the engineer, and then the responsible people, or I think what they said is like in town, in the city of Munich, not all the streets were having lights. People were not having electricity necessarily. So they said, why are you going to build this? Why are you going to build this? And now 100 years later, they're very happy to have already alternative energy turbines. So tell us a little bit more about Siemens Energy. I think it's separate from Siemens, but still connected, related. And maybe you're going to share with us what parts of the energy market that you play in.
Yeah, so Siemens and Siemens Energy, we were one company. So I was hired in Siemens AG 10 years ago. And in 2020, they decided to divide this into two companies. So Siemens AG, they still hold like the trains and the digital industry, where we collaborate closely together. And Siemens Energy, we have all the transmission business, so smart city business. We have electrolysers to convert electricity and water to hydrogen. And we have gas turbines and wind turbines, which are our main business. Yeah, and we really care about also the energy transition. And here gas turbines play also a big role because they are reacting very quickly. So with this renewable energy revolution in like countries where you have a lot of sun and it's hot, the people are going home. The sun goes down and suddenly you need a lot of energy at evening to power up all the air conditioning. And here gas turbines play a vital role. So in all the countries, so even Saudi Arabia, Texas, or California, they all need gas turbines, even if they are blessed with a lot of sun and wind. And yeah, also in Germany, the gas turbine demand needs to be high because we know we have periods of up to 2 weeks where there's virtually no wind, no sun. And then you need a resource which is reliable. And you can power gas turbines in 2 different ways. So one is the combined cycle where you add a steam turbine at the end. There you can reach up to 65% efficiency with our best 9000 HL turbines. And a single cycle where you just power the gas turbine and you can react very fast. You can just turn it on for 1-2 hours and then turn it off again.
Okay, thank you very much for that. Just that, some of you listeners will have known that, but some, and including myself, maybe have not been that aware. I think I'm going to ask you one final question on what should if we're talking a gas turbine, it's a huge thing. What is the size? What should I think of when I see pictures?
Yeah, so the size of a gas turbine could be like a Berlin double-decker bus. It's 12, 13 meters long with a diameter, I think, of up to 3-4 meters. And the nice thing about gas turbines is they have a lot of power in a very concentrated space. So one gas turbine can generate 300, 400 megawatt of electricity, and this you can build in one building. Compare this with wind turbines, where the biggest onshore wind turbines have 6 megawatt and have a length of 200 meters. So you need a lot of them with a capacity factor of 20%. That's a typical capacity factor here in Germany.
Okay. That's like a factor, factor 80 or something like that.
Yeah, so if you want to replace like 300 megawatt gas turbine fully with wind turbines, you have to multiply it by 5 and then divide it by 6, and then you know the numbers of wind turbines you need.
Good, thank you for that. Today we're talking about the acceleration of the design process. I assume that we're probably going to use the gas turbine as an example. And your claim that I've read is that integrating machine learning into the design process has the potential to decrease the computing time from days down to minutes. Maybe let's start that you explain us how today or how yesterday your design process worked, and then maybe you're going to tell us how you're changing it.
Yes, so we introduced gas turbines with an efficiency of 60% in the year of 2000. And since then, we increased efficiency up to 5%. And every time you increase the efficiency by 1%, you have to get 100 degree hotter turbine entry temperature. The thing is, we haven't found any metal, our competitor, also not any metal which just can hold 500 degrees Celsius without melting. So we need a lot of very complex geometry and cooling technologies, coating. And then you need a lot of simulations to verify that all the disciplines you need to calculate to verify that the turbine blade fulfills it is increasing exponentially. Like in the year 2000, we did hundreds of calculations, and now we have to do 100,000s of calculations in all disciplines like CFD, FEA, conjugate heat transfer.
Tell us one or two of these acronyms, what they stand for. FEA, for example?
Yeah, FEA is finite element analysis, which is used for structural mechanics. There we have very time-consuming elastoplastic calculation, which takes on our best computer cluster up to 70 hours. And CHD is conjugate heat transfer, where you use CFD to solve the energy equation with the fluid and the solid to get very accurate temperatures. And here we have to be very, very accurate. So you need a very fine mesh, which is very time-consuming. and CPU intensive.
Okay. So what is the tools you use for exactly accelerating, you say, where maybe in the past you would need it days, you can do today's in minutes. Are they internal tools? Is that products you only use yourself? Are they tools that are designed by maybe Siemens themselves and they are available on the market, or what are they exactly?
Yeah, so every gas turbine development, we have a combination of commercial tools and in-house tools. So you have in-house tools which build the geometry of the turbine blade, and then commercial tools like ANSYS, StarCCM, Abacus, they just help us to do the simulation. So they are very computational intensive. And then in the last 10 years, we introduced process chains. So before it was always one designer is doing the aerodynamics, the second is doing the thermodynamics, the third the structural integrity test. But now we combine this more into a process chain so we can calculate all disciplines at once, which also takes a lot of time. Yeah, and then here we introduced our first machine learning models to surrogate some of these disciplines piece by piece.
Okay. What type of machine learning are we talking about? Can you not go too detailed, but at least at the level of, are we talking, what kind of machine learning? Is it reinforcement learning? Are we talking generative? What is it that you're doing, that you introduce simulation? I think you talk about the simulation process. Simulation has been done a long time, even when I started computer design 40 years ago. But what is it that machine learning is changing, so to say?
Yeah, so even 20 years ago, there were some simple surrogate models, very basic linear or polynomial surrogates, which you can replace basic scalar relationships piece by piece. But now we explored. So we had a competition here at Siemens. It was called Innovation Fund, and then we applied for it. We pitched in front of the CEO, and then we won small budget to explore a lot of technologies. And there we tried all kinds of machine learning models which were suitable, like random forest, CNN, BNN, so Bayesian neural networks, and we just tested which of them gives us the best prediction with the least amount of training data.
Uh-huh. And can you share with us which one was the winner, or is that internal information you would rather want to keep internal?
Yeah, we published some papers about this.
Oh, you did? Okay.
Yeah. I mean, lots of good models were Bayesian and the Gaussian process. They were both quite good. And then what was also very important is that these machine learning models could predict their own certainties. So you could ask the model, what efficiency will this turbine blade have? And I can say, okay, 90%, but I am very confident, or I am not confident. And if it's not confident, we say, okay, then we need more trainings members. So we need more simulations to make the model more confident. And the nice thing is about this model is, you need to create simulation data for weeks, train for minutes, and then the predictions is in seconds, milliseconds. And suddenly you could go from 1,000 members to 100,000 members.
And then you can upgrade the probability or the probability of the model that it says itself. So, and then at a certain point you're going to be happy with, I don't know, at 90%, or where's it's a very general question. It's always asking yes, as you say, we're working with probability, machine learning, probability Bayesian models, Gaussian models. At what point is then there the cutoff where you say, okay, now we're not going to put more effort into because we're happy with X percent?
Yeah, this is case dependent. This is really case dependent. Sometimes we are happy with 98%. Sometimes a very intensive calculation, we say we are happy with 90% confidence. It's really case dependent, and then really also what is the optimization criteria.
Now, interesting that you mentioned both the Bayesian. I recall Bayes. Is it what was his name? Pfarrer. Well, I forget the term now. It was a kind of priest, right? Bayes or Gauss. they are all, I guess we call them part of the machine learning, but they are approaches that are not from the last couple of years, right? I mean, we've been doing they for many years now, and that is the question. On one hand, you call them out specifically, and I understand they help you, so they help you move forward. Then now the other, I'm going to combine the question with what about, newer approaches like generative design, whatever the base of those approaches is. Is that something that you're looking at as well? I mean, does generative have a role to play in, again, accelerating the simulation design process?
Yeah, exactly. So these are our newest research projects where we look into generative design, also on 3D surrogates. So a surrogate model where you can just give any geometry and then it can give you all the predictions you need. But this is really the newest type of technology. And then here we see also all the small startups which are building the surrogates. So they all have different models. They all have different approaches. So nobody has found now this is the right way. So this is still in, I think, explorative phase. So where every company is testing what is best. Also, we are testing it with some PhD students. They just use different models which have been used for complete different applications like image recognitions or some biological like medicine applications. And then we used it on simulation data. Sometimes they were very successful, sometimes not. But this is something we now have to explore. And I really believe in 3-4 years, we will be in a stage where with some small piece of training data, you can build like a generative AI model, which can do all the predictions, which takes weeks, seconds, minutes.
Now, when you talk about predictions, I'm going to ask you a question that turns it almost the other way around. It's like you just mentioned, I think, healthcare. So I'm not sure if we're then talking reinforcement learning. I think we call it still generative, but it's like, so designing the new proteins, right? And I know what the outcome needs to be. So I have a number of variables. Whatever that is in healthcare, I have no clue, but there's A, B, C, and D, and they need to have specific values because that's the new medicine I'm looking for. Now, my question, of course, then is going to be, and we heard from you, what it is that you need to do is improve efficiency from 60 to 65. So you still have 35% ahead of you for the next couple of years.
Yeah, there's a Carnot limit. So
yeah, I can imagine.
100%. So there's a thermodynamic limit.
Yeah, I understand that. But nevertheless, so the question then is, do approaches exist? And because that would, in my understanding, typically be generative to say, I need an efficiency of, let's be realistic, 68%. And you tell me how the design looks like. So it feels like the other way around. Does that exist? Does that make sense?
Yeah. So we have optimization criteria. Yeah. So you could say, okay, let's push it to, 67, 68% efficiency, and then see what is the condition and to determine rate. So you can push the temperature quite easily with simulation up, and then you have to verify that all the other disciplines hold. And this is the difficult part. So you have your metal geometry, you have your coatings, you have your coolings, and then you have to do all the simulations and then verify all the disciplines. So you have aeromechanical discipline, elastoplastic discipline, and all these disciplines needs to be into our review criteria because our customer want to run the turbine for years, not replace it after every year run.
You don't want to have it to be the size of 2 buses. It should still be the size of 1 bus or smaller, I guess.
Yeah, even more compact would be nice. Yeah.
Okay, maybe if you can walk us through a number of applications. So I believe it's one step more detailed. Tell us a little bit about, what exactly it is that you do in the different approaches, maybe how you do it. We just talked about different approaches. Is that something you can do?
Yeah, so now we have this collaboration, Siemens Energy and Siemens DI. There's a tool called Heats, and Heats, you build workflows. So you can couple your geometry building tool with your CFD tool, with your FEA tool, and do simulations. And here we developed together a tool called HEATS AI Accelerator. And HEATS AI Accelerator works in this way that you run your process chain on the classical way. So you do simulations, which takes a lot of time. And after 100 member, the tool automatically checks, builds a surrogate model, and says, can I replace the simulation with a given certainty? So it always checks. So it's doing a decider, so inside the process chain. So maybe the member 101 is not good enough, but after a certain time, member 200, 300, 400, you see that the AI replaces more and more simulation. So maybe in the beginning 10%, and later 30, 50, 80%. And then you get a very good boost and you accelerate your optimization by a big factor. This is one tool where we put it in.
Yeah, let's stay there a bit because it sounds magic. That's why I'm quiet. It sounds a bit like, and it's probably not, but even if it's not, you can then correct me. It sounds a bit like, I started looking into chess, and I've probably mentioned that when, what was that, AlphaGo and then AlphaZero, I believe. But that was more about the algorithm only knowing the rules, so to speak. So the rules would be, the rules of whatever, thermo design, the details of your engineering. But then it runs millions, it does millions of games. And at the end, it felt to me a little bit like, it becomes more certain. And then at some point in time, it starts winning. And then it's you can't win anymore from it. Maybe that's a different approach from what you were.
It's a different approach, yes. It's more like you have a surface, and on this surface you have pressure, temperature, and other like results. And then you train the artificial intelligence. What happens if the turbine blade is a little bit leaned, pressure, suction side, or it's thicker, thinner? Yeah, it changes the shape. So we are changing the shape, and we are giving the AI, that happens if we do the turbine blade thicker. Remember that. And then piece by piece, it learns from it. And then after a while, it says, okay, now I'm sure I can predict all the geometric optimization you are doing with the surrogate. And that's the thing. And it's not like chess. You can just train one surrogate and it builds the turbine blade for any engine. You have to retrain every time. So every engine type, 50 hertz, 60 hertz, bigger, smaller, and then also the different turbine components, you have to retrain model.
Very good. You were going to share a third application with us.
Yeah, so the second application, which is really important for us, is also the robust design aspect. So the thing is, with optimization, you can get a very good nominal design. So you can design it on peak performance, peak lifing, and so on. And then it could happen that you are on the response surface on the tip of the Eiffel Tower. So any shaking, any variation on conditions, so you run the engine in Kuwait or in Iceland, is a different condition, or from casting, you always have some variations in wall thickness and so on. So you have to test your best designs on all the variations. And there are a lot of variations. So you have boundary conditions, geometric. So you have to test millions of variations. And again, here you could do it with simulations, but this could take years of calculating. Or train a surrogate, and then the surrogate can give you some sort of robust design response.
Okay. And this is one of the examples where you say this then can happen, within minutes, but a very big factor faster than you could do it in the past.
Exactly, yeah. Several orders of magnitude faster if you trained the model with the right data. And you can get this robust design answer.
Okay, I think there's one more on creep. Is that right? That you can talk about?
Yeah, so creep is a elastoplastic calculation. It takes a long time because you have to recalculate every time step with FEA. So you have to do the calculations thousands of times.
Share with us what is creep, because we did this before. There was a misunderstanding I think, between what I called drift at that time. And I thought we were talking about a running machine kind of slowly moving towards giving data that are different, and the model then starts reacting. But creep is something different, right?
Yeah, so if you have a piece of metal and you heat it, it gets larger elastically, and then you cool it, and then it goes down.
Oh, okay. That's the creep.
But if you heat it too much and pull on it with a huge force, which we are doing on the gas turbine, then you get into the elastic plastic deformation.
Oh, right.
Yeah, and then we have to calculate this inside our design limits.
Okay, that sounds almost like how you produce metal objects or not.
Yeah,
When the steel is fluid or not, you can put it in the form that you want, and then you cool it off, I guess. Or
twin gas turbines are very, very hot.
yeah, right. So creep is then something you can basically say you do not want to happen, or can you say it will happen?
It will happen, but it needs to stay inside the limits, so we can verify for customers.
Okay. And what do you do then to calculate creep now with the new machine learning based approaches?
Yeah, so again, the same thing. So we do FEA calculations, and we save the data in a specific format. And then now we are testing several models to predict this time-intensive calculations. And then we can do temperature variations, geometry variations, and then the simulation, which took several days on 500 CPUs, can be done in seconds.
That's good.
Yeah,
that's really good.
Yeah.
So then other people can use the same CPUs in the time that you don't need it.
Yeah, exactly. Yeah. So there's always a competition between all the disciplines, combustion, aerodynamic. Everyone wants a CPU.
Yeah. Access to, yes. On one hand, we hear, everybody wanting to buy the, H100 NVIDIA or whatever, it doesn't matter what processor, and more and more and more. We all need to design chips, etc. But at the same time, if you say, we've been using specific approaches and we can now, I don't know what the number is. I just say, is it 10% or 1% of the CPU time to do even better things, then that's almost a development towards the other direction, right?
Yeah, the thing is, in the past, you need 10,000 CPU hours to design a 60% turbine blade. Now you need millions. So the
Okay.
number of simulation hours you need to create a high efficient product goes exponentially up. Yeah, like the CPUs are.
All right. So bottom line, we still need more than, yeah.
This NVIDIA A100, V100, they get very important for model training. So this highly efficient GPUs, we did benchmarks. So on the CPU, it took us weeks to train, and on the GPU hours. So that's why the NVIDIA shares are going up so much.
Exactly.
You need this GPU power for model training.
And of other companies trying to get into that market. I'm again reading Patrick Gelsinger from Intel, but that's another topic we're not going to get in today. We're actually going to come to a close here. Maybe you can share with us what is the status of, the topic of today, applying machine learning to the industrial simulation design process. If you look around the world, you gave already, as you are aware, where your turbines, as an example, are going to be placed in around the world. You talked about California, Saudi Arabia, just as examples. So where are you? Where's your competition? We don't need to know names, but how is applying machine learning to the design process? What is your view around the world? And how is it going to change? How do you see the machine learning into the design process change over the next, the complete way of doing things over the next 5 to 10 years?
Yeah, so in our industry, I think it's in the proof of concept phase. We are using it for some very challenging designs and putting it piece to piece to all designs. And I think all our competitors are in the same phase. So it's getting piece by piece integrated into our design process. Some industries, like Formula One car design, a little bit further. So what I heard is they completely optimize on the surrogate. So simulation is just there to feed the surrogate model with more confidence. And then the optimization is completely done on the surrogate. And this is, I think, the way it will go. Either you make parts for cars, for turbines, for aero engines or airplanes. Data will get more and more important. So you need to save your simulation data and feed piece by piece your surrogate model until your surrogate model can build every piece of your product with a good confidence, and then you can design faster and better. And that's, I think, will be the change. So in the past, there was always you do simulations to design, to verify that your cut geometry is in the right shape and can be manufactured. And I think in the future, in 5 years and 10 years, we will all feed a big generative AI model. And then this generative AI model can be run by experts to do very, very challenging designs much faster.
Let's stay as a final on this very topic. I want to understand. So is this Gen AI model then, is that, some kind of foundation model? Is that an industrial foundation model that we have talked about in the past for the last year? Everybody's talking about it. I haven't seen it yet. Or do you see that while it may be a foundation model as such, that could then be generally available to everybody, at the same time, you're going to fine-tune it as one option, I don't know, with your specific Siemens Energy, and you said Formula One, whoever, and everybody's going to use their, is it then simulation or whatever, engineering knowledge from the last, in your case, 170 years or whatever it is, Siemens. What is the approach there of both the foundation and the specific knowledge?
Yeah, I think it will be a combination of models. So it could be a big foundation model, a large language model, which would help like a complete new engineer to guide him how to design. So it really would answer questions and guide him what steps to make. But I think for all the predictions and so on, it would be really a combination of several variable autoencoders, GNN, MLP models, which together do the best predictions with the data they have.
Right. So still you as Siemens Energy would be able to produce your gas turbine moving towards, I don't know what your goal is. We just heard 60, 65, 70%. And your competition, they would use their own engineering knowledge from and maybe some other ones will use new ways of doing things, but it could be on a common foundation model. Then the question, of course, is who's going to produce such a foundation model? Who has the interest in doing that? Is that, does it need to come from industry, like, from Siemens, and together with competition as far as that is allowed, or who would do that?
Yeah, that's a big question. Yeah.
Okay.
Will we have a lot of models from a lot of startups, or will someone invent a model which can understand all simulation and engineering data?
Let's see who is going to come up with such a model. It feels like the more interviews we do around generative AI, that it always comes up. Let's see who's going to be the first and who's going to be the second, third, if we're going to have this one big, or if we're going to see in the course of the year many different, in our case, interest specifically industrial foundation models. Behnam, thank you very much.
Thank you, Peter.
The listeners, if you want to get into touch with Behnam, you can do that best on LinkedIn. Behnam, Behnam Nouri, Nouri. We'll put his LinkedIn profile in the podcast notes as well. Otherwise, if you, the listeners, have any questions, comments, please send me a short email, peter@aipod.de. I'm very happy that you stayed with us so far. Looking forward to have you with us again. And Behnam, thank you very much and have a nice day.
Thank you.
Goodbye.